So this is part 2 of our Turing Machine Week, Turing Machine lectures. Okay, we're going to be talking about universality of computation, and it's going to be, I think, a fun lecture. Okay, so here are the questions that we're going to be interested in this lecture. Is Turing machine basically the right definition? Here's a picture to keep in mind, right? So we have regular languages solvable by DFAs. We have then the Turing machine decidable languages. That, of course, is a superset of regular languages. We have regular languages there, but also something like 0 to the n, 1 to the n, primality testing. These are Turing machine decidable. And the question is whether this set is equal to solvable with any computing device that you might come up with, you might, construct in this universe, let's say, right? So that question remains. And we will talk about that. Another important question is, are there undecidable languages, right? So we have this Turing machine decidable set. Is there any problem language outside the set? And I would say that it doesn't matter what the, in some sense, the answer to the first question is. Regardless of that, I think the second question is interesting, because even if Turing machine decidable somehow didn't capture all of computation, it's still a very interesting model of computation, and you would like to understand its power and limitations. So this is a very interesting question. And third, how did Alan Turing come up with his definition, right? What was his motivation? And I want to talk about that in this lecture. And in fact, in this lecture, I will really focus on questions 1 and questions 3. I will say a few words about question 2, but not much. And really, next week's topic, next week's focus is really question 2. Okay? So let's start with question 3. What was Turing's motivation? And now we go back to early 1900s, right? We live in Alan Turing's time. We know we discussed Entscheidungsproblem, right? It asked a very important question asked by David Hilbert. And if you recall, this question was the following: is there a finite procedure to determine the validity of a given mathematical statement? Right? And you're given some mathematical statement and you want to know true or false if it, let's say, can be proven, it's provable or not. And here, finite procedure, we now understand that this is asking for an algorithm. But, let's think about what Hilbert might be thinking when he's asking about the finite procedure. Like at the time, what was people's concept of a finite procedure, right? So we have this process, computation in some sense, input data, the output data. In the context of Hilbert's problem, the input data is mathematical statement, output is true or false, depending on whether the statement is, let's say, provable or not. And now what is this, box? What is this orange box here from the perspective of people at the time, let's say? Well, for this, let's think about what does the term computer mean at that time? So computer referred to a person trained in doing calculation. And as we, discussed in lecture 1, computers were people and usually women. And so, the concept of computation at that time was, you have a person, they have a set of instructions, and they're carrying that set of instructions to do some kind of a calculation, right? Okay, so now, if, the answer to Entscheidungsproblem is yes, and there is some finite procedure like this to solve that problem, then it would suffice to basically give a set of instructions and say, look, this is the set of instructions. If you follow it, you'll get the answer that you want. And this doesn't necessarily require you to give a formal definition, formally define what that process is. Some intuitive understanding of what that process is suffices for this task. On the other hand, it was clear that, it became clear over time, I should say, that, the answer was going to be no. And now, if you want to rule out any kind of finite procedure like this and say like, no matter what you do, you cannot solve Entscheidungsproblem, then, that forces you to define mathematically what this process is, right? And that's exactly what happened, right? So mathematicians at the time were like, okay, we have to define this. Let's define this mathematically so we can rule it out for in the case of Entscheidungsproblem. Gödel had some definitions, but he was not convinced he had the right definition. Church came up with lambda calculus, but people at the time did not find that convincing, that, that should be the right definition. And then Alan Turing came along with his paper, and people pretty much immediately were convinced that, yes, this is actually the right definition. Now, then the question is, why was Turing's paper, why was Turing's argument so compelling and so convincing, right? So I want to now tell you about that. And basically, the reason that it was so compelling and it was very convincing is because he took the task head on in some sense. He said, okay, I'm actually literally going to think about a person doing calculation. I'm going to take that process and I'm going to mathematically define it, okay? Which is kind of crazy if you ask me, because like, how do you mathematically define that process? It seems like a very complicated thing. Like, how do you model that? Do you have to model the atoms in the brain of a human being? Do you have to model the atoms in the paper and the pencil? Like it seems an impossible task. And the genius of Alan Turing really is that he was able to, extract out all the messy details, all the distractions, and distill everything down to the essential components, right? They capture the essence of the process in the most elegant and simplest way you can do, right? And that is really the most amazing thing about this paper. Really, the most amazing thing about the Alan Turing's paper is not any theorem proof, but it's actually a definition. It's the Turing machine definition. And now, how did he then, do this? Like, okay, let me now give you some of the arguments that he made in his paper motivating his definition, right? So he said the following: look, a human writes symbols on paper. So when a human is doing computation calculation, they work on a paper, and he imagined the paper as like a squared paper with cells, right? Like a math paper. And he said, look, human being does paper. So in Turing machines, we have the tape that basically corresponds to paper. This is where information is basically stored. Now, the paper, of course, is like two-dimensional cells of a two-dimensional layout of cells. But he said, that doesn't really matter. Like, we can imagine that you have like just one-dimensional sequence of cells, and that would be equivalent. So that's the motivation kind of for the tape. He said there shouldn't be any upper bound on the number of squares that you're sort of allowed to use, or the number of papers that you're allowed to use. And this is something that we discussed last time in the last lecture. Look, if you need more paper, you can always grab more paper to work on. And of course, if I give you like large inputs, bigger and bigger inputs, you will need probably to use more paper, and that's fine. He said humans can reliably distinguish finitely many shapes. So if you look at a particular cell, well, that's some finite region of space. And how many different, symbols can you put there? Really finitely many. So this is his motivation to define the tape alphabet as a finite set, right? A tape alphabet is just a finite set of symbols. What else? He said human observes one cell at a time. And this is basically corresponding to the tape head. You have some tape head, and that's like where the human's focus is in some sense. That's what it represents. Now, you might object to this and say, well, I can observe 3 cells at a time or 5 cells at a time. It's not just one cell at a time. But even if that's true, and of course, you might be able to do that, this is sort of without loss of generality, because if you said, okay, I can imagine 3 cells at a time. Okay, so let's draw those 3 cells. Suppose that each cell can contain, let's say, 2 symbols for simplicity. So there are 2 possible symbols that can be here, 2 possible symbols that could be here, and 2 possible symbols that could be here. What you can do is, of course, you can imagine these 3 cells as one big cell. Okay, and then increase your tape alphabet so that it can accommodate 8 symbols, right? So for every possible sequence of symbols that I can see in these 3 cells here, 2, 2, 2, I'll create a symbol, a new symbol that corresponds to that sequence. So now I have a bigger alphabet, and I'm sort of imagining these 3 cells as like one big cell, and I'm imagining my alphabet being a bit larger. And so if you said like I can observe 3 cells at a time, then I can translate that in a situation where you're observing 1 cell at a time. And the number of symbols doesn't matter. If you have 8 symbols, that doesn't give you extra computational power, actually. That you can translate that back to like a binary alphabet if you wanted to do that. Okay, so that's like another piece. He said the human has finitely many mental states, which makes a lot of sense, of course. You have finite brain with finite number of neurons. But, an interesting way he actually sort of reasoned about this is he thought, as a human being, when you're doing computation, let's say they start in the morning, they carry out some calculations, and then let's say it's lunchtime and they need to take a break. So they pause their computation and they imagine, okay, what would a human being have to write in order to continue the computation from where they left off after lunch, right? And he imagined that, okay, you have to remember which cell you were looking at, and maybe write down sort of your mental state, what you were thinking at that time. But then you should be able to easily continue from that point on, right? He made these kinds of interesting arguments for this. He said a human can change symbol, can change focus to a neighboring square based on its state and the symbol it observes. This is basically the motivation for the transition function of a Turing machine. Now here again, you might object and say, well, if I'm doing computation calculation, I don't necessarily have to just go 1 cell to the left or 1 cell to the right as I'm changing my focus. I might go from this cell here, and then in 1 step to a cell that is further away. And okay, that's true perhaps, but you can imagine going from changing the focus from here to here as a sequence of, okay, I go right, until I hit that square. The point is that this doesn't affect the computational power of the model. And in the spirit of keeping the model as simple as possible, this is like a good way to do it, a good simplification, right? Let's just assume that it goes left or right. And if you're skipping ahead, we can simulate that with just going 1 step to the left or 1 step to the right. What else? And he said humans act deterministically and, so on and so forth. So he had some nice arguments like this. And, when people read these arguments, they were like, yeah, this captures really what a human being does when they're doing computation. So the beauty of this definition, there are a couple of things. One is it's in some sense the simplest model that you can imagine for computation. Because think about it, what is computation? Once again, it's manipulation of information, right? So you do need a place to store the information. That's the tape, that's the paper. You do need a way to read information, of course. So you have the tape head, you can read 1 symbol at a time. And you need to manipulate, right? So you need to be able to change the information. So you can change a 0 to a 1 or 1 to a 0 at one particular time. I mean, any kind of computing model has to have these pieces, right? I mean, without these, you cannot do computation. And really, Turing machine is the simplest thing that does those things and really nothing more in some sense, right? And so it's kind of crazy that that kind of a simple definition captures, computation. It seems to capture computation in its full generality, and that you don't need more. Now, let me say one more thing about simplicity here. So what this means, if you think about how simple the Turing machine definition is, what this means is that any reasonable definition of computation that you might come up with would be strong enough to capture, general computation as Turing machines do, because to capture general computation, it seems like you don't need to actually do much, right? Any process that can basically do what a Turing machine can do, that will be a correct definition. And so this means anyone who attempted to come up with a definition of computation could have accidentally hit the correct definition, right? It doesn't take much. I mean, the only way you don't capture computation is if you're really restrictive, if you define a model like DFAs, which is really like a read-only machine, right? It doesn't have the power to manipulate anything. It's a read-only machine. So if you have some kind of if you make a mistake like that, then okay, you won't capture computation in its full generality. But otherwise, you should be able to, right? So Turing's real contribution here is not that he was able to come up with the right definition, but he was able to come up with the simplest definition that was convincing, right? That it was clear that it actually correctly captured computation, right? And that was what was important at the time. At the time, it was important that we had a very simple definition that convinced people that it was the right definition. And then in terms of generality, of course, our belief, as I said, it's sort of, when you read Alan Turing's paper, he has a section on motivating his definition, you see, yes, it clearly captures what a human does given a set of instructions. And this, sort of belief that it captures computation in this sense is called the Church-Turing thesis. It states, there are various ways to phrase the Church-Turing thesis, but one way is kind of like this. The intuitive notion of computable is captured by functions computable by a Turing machine. And here, the intuitive notion of computable is what humans do when they're computing, right? So basically, the Church-Turing thesis, what it says is that this process here can be modeled by a Turing machine. Very good. So what else did Alan Turing do in his paper? Well, he actually showed that the Entscheidungsproblem that Hilbert asked is actually undecidable, uncomputable, right? So the answer to this question is no. And that's interesting because if you think about it, you can say, well, computer science as a field was born aware of its limitations, right? So in the paper, you introduce the model and you say, okay, here's the model of computation. Same paper, you're able to prove, oh, by the way, here are things that it cannot do. Immediately we knew the limits of computation. And so a picture, again, this picture, to keep this in mind, we have the Turing machine decidable languages, and we know Entscheidungsproblem is outside this set now. But, there's still very interesting questions here, are there others, right? So we know one problem that's undecidable. Are there other problems undecidable? Is it the case that most problems are decidable and there's only a few undecidable problems? Or is it the other way around? What is that divide? How can we understand the divide between decidable and undecidable better, right? So this is very interesting. So there's interesting stuff to explore here. And we're going to do that next week. So I'm not going to say more on this. But what else did Alan Turing do in his paper? Well, we talked about universal machines, right? The concept of a universal machine. This is what I'll call one machine to rule them all. And what I told you is that, look, you might be taking this concept for granted because the computers that you use today are universal machines. They can be programmed to run any kind of an algorithm. This has to be motivated. You cannot just take that concept for granted. And in a world where, there's no universal machine, really the situation is that for every task that you need to solve, you need a different machine, right? So that's kind of how it would be. Right? But now the question is do we really need a separate physical machine for each task? And, Alan Turing realized that no, actually you can, he introduced this concept of a universal machine, which means you don't need a separate machine for each task. Okay. And now the concept of universal machine, perhaps in hindsight, you might say, yeah, that's clear or obvious. But, to sort of see it, to motivate it, I think what you need to do is look at it from the right angle. I think if you look at things from the right angle, in some sense, yeah, you could say it's obvious. If you don't look at it from the right angle, it might be a tricky concept to actually come up with. So my claim, I think the right way to look at this is to actually look at this picture. And then if you modify this picture here a little bit, then you can see the concept of a universal machine emerge. So who can tell me how to modify this picture and then which will allow us to see a universal machine? You basically take the instructions here and you view them as input to the process rather than being sort of hard-coded into the process, right? So you're just taking the set of instructions and viewing it as input. And then you ask, if you view it this way, you ask, what's the role of the human in this process? What's the human doing? Well, they're taking a set of instructions and input data, and they're just executing those instructions one by one. And here a human is actually playing the role of a universal machine, right? And indeed, at the time, it was not like we had a set of people who did who took logarithms, and then we had another set of people who took derivatives, and we had another set of people who did, integrals or so on. No, right? One human being, one day they might do logarithm, the next day they might do a derivative, so every day they might do a different kind of computation. What is important is that they get the precise set of instructions to be able to carry out that computation, right? So a human being there is like a universal machine, right? And what makes this possible, the key sort of concept, the key idea that makes that universal machine possible is the fact that, instructions or these Turing machines are encodable, right? Because when you think about it, the set of instructions, we are viewing that as input to the process, input to a computation. But input to a computation has to be a finite length string. So as long as, those instructions, or as long as a Turing machine has a finite length string representation, then we can sort of carry out this process, we can see it as proper computation. So the key idea is that Turing machines are actually encodable, right? And what's an encoding? What's a string representation of a Turing machine? Well, I told you, you can think of Turing machine as a piece of code in some restricted programming language, something like this. And if you just take this text that you see here, the string, you can view this as the string representation of a Turing machine, right? So then, right, the key idea here is code is data, right? If you're taking 150 there in that course, they will say functions are values, right? So in 251, our version of this is code is data. Okay, it's the same principle. And this makes a universal machine possible because now we can view code like a Turing machine as input to another piece of code, a universal machine. So we have a Turing machine here as input, the encoding of a Turing machine, and we have some X which is supposed to be input to this Turing machine. The universal machine's role here is to simulate this Turing machine on that input X and then provide the output that that Turing machine would provide, right? And this universal machine is a Turing machine itself, okay? So you can actually come up with a Turing machine, which is a universal machine. Now, how can I convince you that this is actually a Turing machine? Well, there are several ways I can do this. For one, I can ask you, like, imagine that you're living in early 1900s and your job is to be a computer, right? And you come into work and I give you a description of a Turing machine on paper, right? Just like in the previous slide. And I give you an input X that's supposed to be fed into that Turing machine. And I ask you, can you please simulate this Turing machine on this input and tell me what the output is going to be? Can you do that? Of course you can, right? So you take a piece of paper, I mean, you have the states, you go through the states one by one and simulate it. I mean, we've done Turing machine simulations, like in previous lecture, I've done it on the slides. You can easily, of course, do this. And so if you can do this, then a Turing machine can do it because a Turing machine is modeled precisely. You know, it's a mathematical model of that process, like of a human being carry out certain instructions. So there's a Turing machine for this. But maybe if you don't really find that convincing, think about, you know, can you write a Python function that does the job of a universal machine, right? So you need to write a Python function that takes the description of a Turing machine as an X as input and then runs that Turing machine, simulates that Turing machine. I hope you agree that, yeah, of course you can do it. Like you have to parse that string, which represents a Turing machine. You can load that information into appropriate data structures, convenient data structures. And then once you have that, you can start simulating it on some given input X, right? That will be that wouldn't be too hard to do. It could be like a homework question in 251, for example, right? Because the syntax of a Turing machine is quite simple. And if there's a, you know, if there's a Python function to do it, there's a Turing machine to do it. Python function boils down to machine language, and machine language, like a Turing machine, can simulate that, right? And if you think about it, this is exactly what like a Python interpreter would do, right? I mean, a Python interpreter does not take in a Turing machine description as input, but it takes in a Python program and Python function as input and some other X that's supposed to be input to foo.py, let's say, and it will run, it will interpret, it will execute the instructions of foo.py given the input X and then give you the corresponding output. So this is what the Python interpreter does. And if you don't find any of this convincing, well, I might say, okay, well, you can Google like a universal Turing machine and, you know, you'll see an exact like description. Like people have come up with universal Turing machines and they're not even, you know, that complicated in terms of the number of states they have. You need maybe a dozen or so states to do this. It's not actually that complicated. Okay. So that's the idea of a universal machine, and what makes this possible once again is that code is data. And now there are a couple of different sides of code is data, the consequences. On the positive side, as I said, you have the notion of a universal Turing machine. So great, you don't need a different machine for each task. Our laptops are basically a physical implementation, realization of the concept of a universal machine, and we can run any program on these machines, right? So you don't need a different physical devices, you only need different software. On the negative side, the fact that, you know, code is data can lead to interesting things, like you can do self-referencing things, and you can, for example, feed the code, the source code, the encoding of a machine as input to itself. That's what I mean by self-referencing. And if you recall Russell's paradox is about like creating a self-referencing set, defining a self-referencing set, which breaks mathematics. And similarly, you can define a self-referencing code, which will break computation. And now the consequence of that is not that, you know, mathematics breaks, but the consequence of that is what you can show is that some problems are actually undecidable, uncomputable. And actually, let me show you what I mean by this very quickly self-referencing thing. So here's a piece of code that I wrote, is recursive. Now, this as input takes the string representation of some program. So the program could be something like def f of x return x. So it takes a string like that. And what it's supposed to do is check whether this function, this program is recursive or not. Now, don't look at the logic of this, but basically it's checking if the function is calling itself or not. But it's not even, I mean, it's buggy, but the logic is not important here. So I didn't bother like writing something elaborate here. But, you know, imagine that there's some code that checks if the program is recursive or not. Now, if I run this, so I run is recursive on this program here, right? If I run this, you'll see it will say false, of course, because it doesn't call itself. If I change this to f of x, this will say now true because it calls itself. Now, the interesting thing I can do here is I can take this and copy paste it here. So now program represents the encoding the string representation of the isRecursive function. And now when I call isRecursive program, I'm really calling isRecursive on itself, right? I'm giving as input its own source code. And then if I can run this, right, there's nothing wrong with this, and it will say false because isRecursive is not a recursive function. Now, you know, typically you would not do this, kind of like a weird thing to do perhaps, but it's possible to do it, right? I mean, I just did it to show you that, you know, it's allowed. And this is, yeah, this is basically what I mean when I say, like, you know, self-referencing. You can create self-referencing situations which you can then use to basically break computation. And we'll see that next week. Okay. And yeah, so all of this you can find in Alan Turing's paper from 1936, right? In this paper, he introduced string machine model. He introduced the concept of a universal machine, universal Turing machine, and he also showed that the Entscheidungsproblem is undecidable. In fact, the title of the paper, as you can see, is Uncomputable Numbers with an Application to the Entscheidungsproblem. Okay, I definitely recommend that you take a look at this paper. It's pretty readable. It's very nicely written. So now, the next thing I want to talk about is discuss the relationship between computation and physics a little bit. And the subtitle here is perhaps Turing and others weren't, you know, ambitious enough. So Alan Turing, of course, when he was thinking about, you know, modeling computation, he is imagining a human being doing computation, and modeling that is, of course, fantastic. That's great. But, you know, what about if we go beyond that, right? What if I ask, like, in nature, you know, what's happening in black holes? You know, what kind of information processing can happen there? And can that be, you know, modeled? And how can we model that? Right? So that's, in some sense, a more interesting, a more far-reaching sort of question. And so to explore that, we need to really talk about the relationship now between computation and physics. So what is the relationship between computation and the universe and the laws of physics? Well, it's a bit complicated. The reason it's a bit complicated is because even though, like, in physics, we have very successful theories, like, you know, we have quantum physics that, you know, really, you know, accurately, nicely model the behavior of tiny particles. We have general theory of relativity that, you know, beautifully models the behavior of large particles and gravity. That's all great. On the other hand, we don't have a unified theory. And actually, we're not able to, like, sort of combine these two seemingly separate theories into one. And that's, like, one of the main goals right now in physics, is to come up with, like, what people call a theory for quantum gravity. We don't have it quite yet. And there are other, like, unexplained phenomenon. So given that, of course, you know, we don't know exactly the relationship here, given that we don't have exact, you know, absolute laws of physics. That being said, you know, we still do know a lot. So based on what we know today, we can say some intelligent things about this, right? Now I'm gonna look at this from a couple of angles, right? So one is, how does our understanding of physics influence computation and our understanding of computation? And in the other direction, how does our understanding of computation sort of influence our understanding of physics and laws of nature? Right. So first, let's discuss like physics to computation and what the laws of physics mean for computation. And maybe the biggest question or the most interesting question here you can ask is, if I have some problem that I can solve by some physical process, only constrained by the laws of physics, right? It might be like something that's happening in black holes, or it could be something that's happening in the tiny particles like electrons and photons. Can we say that this process can be captured by a Turing machine? So like solvable by any physical device. Is this equivalent to solvable by a Turing machine, right? And the answer is our belief, most people, I should say, believe that the answer to this is, perhaps surprisingly, yes. Okay. And this brings us to Church-Turing thesis 2.0, right? The more advanced version of the Church-Turing thesis, which is also known as the physical Church-Turing thesis. And it says that any computational problem that can be solved by any physical process, only constrained by the laws of physics and nothing else, can be solved by a Turing machine, a probabilistic Turing machine, probabilistic in parentheses, though I don't want to get into that distinction between deterministic, probabilistic. Let's just say, Turing machine. Okay, so now, why do we believe this, right? Now, I should say, look, it's not like this is... I'm sure you can find people who would disagree with this statement, but I think many people would agree with it. So what are some reasons that we can give for the physical Church-Turing thesis? Now, I'm not a physicist, I should say, okay? So, I'm just sharing with you what I know, but, that's a disclaimer, I guess. I'm not a physicist. So there are at least a couple of things we can say here. One is that if you look at our physical theories, even if you look at Newtonian physics, quantum field theory, general theory of relativity, and so on, these are computable theories. They seem to be computable. Physical systems, physical states can be represented by a sequence of numbers, an array of numbers, perhaps large. And the way these states evolve over time are modeled by differential equations or some linear transformations. And those rules are computable. And this is precisely why we can actually compute using physics in some sense, right? With using our physical theories, we can make predictions and then test those predictions. How can we do that? Because we can compute ourselves as human beings. We can compute with these theories and predict, if a system is in this state now, in one time unit, it will transform into this state and so on using the laws of physics. So, if you model things properly, it seems like laws of physics are computable. Another piece of evidence for the physical Church-Turing thesis, a nice one, is what's known as the Bekenstein bound. And the Bekenstein bound basically puts an upper bound on the amount of information that a closed physical system can have. Okay, so there's some number, it's a big number, but nevertheless, there's some finite number, and it says given some space, that space can contain at most this much information. And then, so this is basically suggesting that, it's a good suggestion that the fabric of reality is really discrete, right? And so that's another, good piece of evidence. So given these kinds of things, and people who understand physics would, I'm sure, be able to say more. We believe that the physical Church-Turing thesis is actually true. Now, let me note here that this is not a mathematical theorem, right? Because this is a statement about physics. This is a statement about the universe, the laws of physics, which is not a mathematical statement, right? It's just saying, it's kind of like similar to saying, let's say, the cosmic cosmic limit for speed is like the speed of light. Okay, so you cannot travel faster than the speed of light. You cannot prove something like that. You can maybe disprove it if you can do experiments and observe otherwise. But these kinds of, physical postulates, they cannot be mathematically proved. You can gather more and more evidence. You can see that it fits to our other known theories. You see that any attempt to disprove it fails. And, after all this gathering of evidence, at some point you take it as a sort of fact. Okay, but it's not a mathematical theorem. I want to point that out. Now, it is very surprising, of course, in some sense, that Turing machines are able to do this kind of thing, and yeah. So in a way, Turing machines seem to capture the computational capacity of the universe. But at the same time, actually, in another way, they don't, in another important way. To understand this, let me actually give you an extended version of the physical Church-Turing thesis. Okay, and this states, what can be computed efficiently in this universe by any physical process or device can be computed efficiently by a Turing machine. So, of course, computational complexity is important. If you want to really capture faithfully the computational power, the computational capacity of the universe, you have to really think about complexity theory, right? It's not just about what you can compute in principle, right? Because if you have a physical system, let's say, and you see like in 1 second it's able to do something, and now with a Turing machine, if you wanted to simulate that, it takes like the age of the universe to simulate that 1 second that we see in the universe. Well, then that's not an accurate, like a faithful way of representing computation, right? So you have a huge loss there. So really, we have to talk about computational complexity, and you want to capture things faithfully in this sense. And now if you ask, like, do people believe the extended physical Church-Turing thesis as stated here? The answer is no, okay? So yes, in one sense, Turing machines are a good model. In another sense, though, maybe in a more important sense, they're actually not. And this is because we do not believe that Turing machines can efficiently simulate quantum systems. They cannot efficiently simulate the behavior of electrons and photons and things like that. Now, this does not mean that the extended physical Church-Turing thesis is fundamentally broken. It just means that you have to actually update it. And rather than talk about Turing machines, you have to talk about quantum models of computation. So you have to turn the T, what I did here is turn the T into a Q. And that, of course, makes sense because the world, the universe is quantum mechanical. And so to sort of faithfully capture computation in this world, it makes sense that your model of computation is also quantum mechanical, right? And yeah, so, and this is important. And this also highlights that if you want to come up with an accurate, faithful model of computation that captures, the computational capacity of the universe, you really need to know physics, right? Like, you need to know quantum physics. And then your model of computation then is going to be based on our understanding of quantum physics, right? So that's important. But nevertheless, this is now what I would call the grand unification simplification of computation, right? So whatever computation that you can imagine, whatever computation that you can express in your favorite programming language, whatever computation a human being can do, whatever computation you might see in a black hole or like some tiny particles doing, all of this, boils down to a Turing machine. And, and if you care about, of course, computational complexity, then, it's quantum model of Turing machine. Okay, and this is our grand unification theorem in some sense, or grand unification result. theory in computer science. Similar to like in other fields, like in biology, let's say you might say the theory of evolution is a grand unification theory, right? So it's a simple theory that explains a lot. And our grand unification theory is, I would say, the Church-Turing thesis or the extended Church-Turing thesis. Okay, so what are the implications of this? Well, one implication of this is that it means studying the power and limits of Turing machines or like quantum machines is actually equivalent to studying the power and limits of our universe in terms of its computational capacity. Or in other words, if you, for example, prove that there's some problem that is undecidable, okay, then that problem is just uncomputable in this universe. Like you're not going to be able to come up with any kind of computing device, whatever you use, even if you use black holes or electrons or photons, it's just not going to be computable. Okay, so that's very interesting. And an interesting question that you can think about here is, can you come up with laws of physics that would allow it to compute any problem, right? So you might think about that. Another implication is that computation in its full generality is everywhere, because if you look at the Turing machine, the model, the computational model, it's so simple, right? It's super simple. So even in extremely simple systems, you can actually find the capacity, the general capacity of computation that our whole universe has. And that's actually very interesting. I will say more about this, but like here's a simple question that you can ask, a very interesting question. What is the simplest universe you can create that has the same computational capacity of our universe? And I will come back to this question. In fact, I will end the lecture with this question, but let me move on now. The third one is kind of a philosophical musing in some sense. You know, this suggests that the universe may be a simulation. So how many of you have heard about the simulation theory? So yeah, simulation theory, if you know, like Elon Musk is a big fan of the simulation theory. I myself, I'm also a big fan. Let me describe it to you like the way maybe Elon Musk would describe. So if you look at the types of games that we were creating in the 70s, 80s, like something like a Pong game. And now if you compare that to the games that we create today, which are so much more realistic, and if you look at that progress, like we've progressed a lot, and if you sort of extend that progress into the future, well, you can say like, look, in the future, we will be able to create simulations games that will be indistinguishable from reality. And I don't think this is a controversial point. Like we might disagree on when that's going to happen. Like you might say it's going to happen in 50 years. I might say 100 years. Someone else might say 1,000 years. But I don't think it's controversial to say that this is going to happen. Now, even if it's 1,000 years, this is, you know, peanuts with respect to like the cosmic time scale, right? You know, the world is like billions of years old. So now the question is, of course, if we know that we will be able to, in the near future, create these sort of universes, which will be indistinguishable from reality, then how do we know that we do not live in one of these simulations ourselves, right? So that's an interesting question to think about. Now, one way to argue against simulation theory would be to say, oh, look, the laws of physics, they're not computable. So if physics is not computable, laws of physics is not computable, that would be like a decent argument against actually simulation theory. But by physical Church-Turing thesis, we know actually the laws of physics is computable. So then you cannot make that argument. And I think what makes this simulation theory sort of compelling is that, you know, the fact that we will be able to create, we know that we will create these universes that are indistinguishable from reality, and there will be agents, you know, sort of in that universe that will be able to, you know, ask the same questions that we ask now, like, are we living in a simulation? And, you know, if they come to the conclusion that, oh no, simulation theory is not a good theory for whatever reason, then we'll know they're wrong, actually, looking from the outside. right? So the fact that this kind of a future is going to happen is, I think, interesting. Though of course you can also think about the arguments against it, right? So I think there are also interesting arguments, potential arguments against this theory. Another interesting thing is that, of course, if we create these universes and then those agents in those universes create their own universes and they create their own universes, the question is, what level in the hierarchy are we at, right? So there seems to be like nested simulations going on, perhaps. Okay, some fun things to think about, but let me actually say a few words now about going the other way. Like, how does our understanding of computation sort of in some sense impact physics itself? And for this, you just have to realize, like, think about what computation means. Like, computation is about information processing. And what is information? Information is a very fundamental property of physical systems. It's sort of measuring the number of possible states that a system can be in. And computation is about how information transforms, changes over time. And then what is physics? Well, physics is about physical systems and the transformation laws, how these systems evolve, transform over time. So you start to see the connection there, since information is such a fundamental property. How it changes over time is a fundamental component of laws of physics, right? So if you imagine computer science, computation as what's going on in your laptops and phones, and like that was your concept of computer science, then it will be hard for you to make that connection between computation and physics. But if you see computation as this general phenomenon of information processing and you understand how fundamental information is, then you start to see this connection more clearly. And in fact, I think, people see this more and more clearly every day. So in the last, 5 minutes or so, 10 minutes, I just want to tell you about this final musing. Like, what is the simplest universe you can create that has the same computational capacity of our own universe? And a very fun, actually, universe to consider here is, I'm sure many of you have heard of this, Conway's Game of Life. Okay, Conway's Game of Life, you can think of it as some very simple universe that consists of cells. Each cell is black or white. So black means that it is alive, white means it is dead. And there are very simple laws of physics in this universe. And let me tell you the laws of physics in this universe. First law is the loneliness law. So if you have a live cell with fewer than 2 neighbors, then it actually dies in the next time unit. There's the overcrowding law, which says that a live cell with more than 3 neighbors dies. And of course, you need a way to create new life. And this is the third now law of physics, procreation rule. If there's a dead cell with exactly 3 neighbors, then it will get born. Okay. So now with these laws of physics, you can have like different patterns, of course. You have stable patterns that, basically don't change at all. The top ones are stable. You have periodic patterns, like, for example, this one here, these two are periodic, as you can see. Like they just periodically change between 2 states. And then there's also like moving patterns. This is like actually called the glider. Well, it's gliding like that. Okay, so now actually let me show you a very quick demo here. So here is a game of life simulator. I can start this, hopefully, and we can see how it goes. And so interesting patterns can emerge over time. Things can die out. Things can continue forever. And yeah, it's kind of very interesting. You can like watch this for minutes and minutes and see what kind of interesting patterns and shapes come out of this. Okay, so yeah, so let me stop it there. Okay, so now let's ask some interesting questions. One question is, can a Turing machine simulate any instance of Game of Life? And what do you guys think? Can a Turing machine simulate a Game of Life? Yeah, and why? Like, what's a good argument to make there? A simple one. A simple argument is we just did it, right? I mean, I just showed you a simulation on my machine of Game of Life, and you know, my machine is a Turing machine at the end of the day, right? So that's a simulation of Game of Life. Now we can ask, can Game of Life simulate any Turing machine? And if it can, you know, it can simulate my machine. That would be quite remarkable if it could do that. And the third question is, can Game of Life simulate Game of Life itself? Okay. And so to end the lecture now, I'm going to show you two videos to address the two questions, the second and third question here. Okay, so let's start with the first video. So here's, we're seeing some cells. Now it's zooming out. Now we see a tape and a tape head with a control sequence. And that's actually, folks, a Turing machine. This is the tape and the states of a Turing machine. So that seems like Game of Life can simulate the Turing machine, right? So that means like Game of Life has the full computational capacity of our universe. Let me now end with another video. Can Game of Life actually simulate Game of Life? And yeah, so those cells have no idea they're in a simulation, right?